Dear colleagues, dear friends, I want to start by wishing you a happy new year. All the best to you and your families, and to welcome you to the first talk of the 4th season of our seminar. We started the seminar in April 2019, and it's still online. We are still optimistic that we will be able to meet in person, hopefully this year. Let's see. So the 4th season is focused on talks given by young colleagues, by colleagues on early career stage. And today's speaker is a young colleague from the University of Southern California, Meisam Razaviyayn, who received his PhD in 2014 from the University of Minnesota. And Meisam spent 2 years at the Stanford University on a postdoctoral position and moved in 2016 to the University of Southern California on an assistant professor position. He is the recipient of many best paper awards issued by different societies in different areas, in signal processing, optimization, in data science. He's mainly working on optimization, but he's very much interested in many other topics, and considering many interesting applications in his research. So, Meisam, thank you for accepting our invitation. You have 45 minutes for a talk.
All right. Thank you very much for a nice introduction. Can you see my slides?
Yes.
Okay, very good. So today I'm going to talk about learning with non-convex MinMax optimization. This is I'm bringing parts of different papers together. This is a joint work with many different people. As you'll see, I'll list the references at the end of the talk. And this is mainly about MinMax games or optimization problems of this form. So if we are interested in solving MinMax game or optimization of this form, okay, I'm going to make some assumptions at the beginning. Basically, I'm going to assume that sets are closed and convex, the constraint sets. The objective functions, I'm going to assume that it's smooth with Lipschitz gradient, but it is possibly non-convex. So basically, the non-convex case is the difficult case. Although some of these results and ideas can be extended to a stochastic setting, although we are considering a deterministic setting, and some of them can be extended to non-smooth setting as long as, for example, your function is proximal friendly. So, and the goal of my talk today is to talk about why is this problem important, basically talk about some applications around it, and talk a little bit about why is it challenging, and some algorithms and ideas and discussions around solving it. So, and please, at any time, feel free to stop me if you have any questions at any point during the talk. So let me start by, so basically I'm going to show, for example, in some particular cases, it's easy actually, it's doable to find certain stationary concept. For example, when your F is strongly concave in alpha, when there is a small decoupling or weak decoupling between the two variables, or when the radius of the set A is small, we are going to talk about in these cases, you can solve it efficiently, up to stationary points efficiently. But before going to into details, I want to talk about first, why is this problem important? So MinMax optimization problems are generally important because whenever you want to design a robust system, you're dealing with the MinMax optimization. In particular, when we are designing for a nominal value of a parameter, we may measure some value alpha naught, and we may design our system based on parameter theta. But when we don't know the value of alpha exactly, we may go after the robust design, which we need to solve a MinMax optimization problem. An example of it is massive MIMO applications that you are designing, for example, the transmission strategy or what beamforming strategy you need to use, or in other words, you want to see how much power you want to transmit on each signal, but your power depends on the channel. So H here is a channel, so people are moving, the entire system is changing, so channel is uncertain. So we go after the robust design. This is one example of, for example, minimizing the cost, but we don't know exactly the channel value or what is the exact position of people. They may move like in 1 second, 2 seconds, but you want to have a transmission strategy that works well against a certain set of channel values. Another application of robustness is in recent adversarial attacks to neural networks application. You have seen probably this image a lot recently. So this is an image of a panda that is classified with high confidence with the neural network, 57%, for example. Confidence 57% is relatively high because you have more than 2 classes. You have a lot of classes, so 57% is a high confidence for the network. But if you add a very small value to your image, a small noise to your image, so if you add this noise multiplied by this value, which becomes a very small added noise, your neural network may classify it as something else, completely something else, with a very high confidence. This is not because of pandas or gibbons. You can basically deceive neural networks to classify anything to any other thing than regularly trained neural networks. For example, in this example, this is for classifying MNIST digits. So the goal is to classify digit 0. These are all digit 0, but they only change a little bit in like different pixels. So if you look very closely, they are a little bit different, but the neural network classified this one as 1, this one as 2, this one as 3, and the last one as 9. So you can deceive the network to whatever you want. And the natural defense mechanism or natural approach, natural remedy for it is to go after a robust training of neural networks. So instead of training for the input, you tune the parameters of the network, which is theta, so that they work also when you change your input, which is alpha. Let's say the input images are alpha. You want, even if your input changes a little bit, your network still works well. This is another example. And the third example is, for example, in GANs, generative adversarial networks, that has applications in generating samples that look like real samples. So examples are changing images to different styles of painting, Monet or Van Gogh. And in this application, we need to find basically a function g that transforms a random variable z to another random variable g of z that has similar distribution as the distribution p of x. So g is parameterized by a network, so it's within a class of functions. We want to find a function that, after applying that function to z, our new random variable gz has similar distribution as the distribution px. And there are different formulations for it, but a very successful formulation for generative models is GANs, generative adversarial networks, which was proposed by Goodfellow in 2014. And the idea was that, the idea of that GANs is to train 2 networks actually instead of 1. One is the generator, the other one is discriminator. The generator is G function. The discriminator tries to basically discriminate G of Z samples and X and classify whether they are different or not. So basically this D and G are competing against each other. The objectives are negative of each other. So it naturally leads to a zero-sum game formulation or min-max optimization. There are other formulations for GANs as well that I'm not going to go over it, but they all lead to non-convex optimization problems of min-max form. So I hope so far I have convinced you that some applications that this problem is important to look at. Okay, I will give you more examples toward the end of the talk when we want to evaluate the performance of some of these algorithms that we will talk about. But before proceeding, I want to tell you why these problems are challenging, because you may say that non-convex problems are basically challenging. It's difficult to solve non-convex problems. What brings like this MinMax? It's like something impossible. You add something impossible on top of it, and you say that it's impossible. Now, I want to like take a step back and tell you that why I believe why MinMax problems are more challenging. Non-convex MinMax problems are much more challenging than non-convex problems. Although some of you might already agree. So to understand the differences and challenges, let me compare and contrast it with the regular minimization problem. In the regular minimization problem, we have that we minimize the function h of b. Let's say it's smooth, Lipschitz constant, again, closed convex constraint set. The right-hand side, if you give it to a practitioner, at least regular minimization, they can apply projected gradient descent, for example, using a lot of off-the-shelf algorithms, such as, for example, projected gradient descent. I don't know why it's jumping. And they can get, it's not an exhaustive search, it's not iteration complexity, it doesn't depend, for example, on dimension, it's not exponential search. And it can we can show that it converges to certain stationary concept. One good property is that the objective function improves over the threads for a lot of algorithms. For example, if you start from one point, you can always expect that you get a better point in the next step of the algorithm. And there are known iteration complexity, lower bounds, upper bounds for different algorithms for solving this problem. You can, for example, use gradient descent type of methods, you can use trust region, and a lot of different algorithms. But if you move to the non-convex MinMax problems and you give it to a practitioner, it's not really clear what should we do. A particular popular algorithm in recent years is gradient descent Ascent. That basically the algorithm that is used, you can see it, find it in a lot of practical works, is you apply 1 steps of gradient descent, assuming that's unconstrained for simplicity. 1 step of gradient descent on theta, 1 step of gradient ascent on alpha. And this is basically the dynamics that you follow. This could apply in parallel or series, one after another. But after applying it, for example, you will see immediately that this is not a very reliable algorithm in practice. So basically, it needs a lot of heavy tuning. This is, for example, a screenshot of the iterates that I got, actually my student got, for training a generative adversarial network after tuning the parameters a lot. And he was asking me whether the algorithm is converging or not. And I said, I don't know. By looking at the objective function over iterates, I really don't know whether we are going to any interesting point or not, whether we are improving or not. And it's, in fact, not very difficult to come up with simple examples to show that this method, gradient descent ascent, may diverge even for simple cases that they are convex concave. So for example, for this function, this type of function, f of theta and alpha is equal to theta times alpha. If you apply this gradient descent ascent method, you would go into the spiral behavior and move away from the optimal point, which is at the center, which is at the origin, which is the optimal point, and you move away from it. You can, by the way, to make it well defined, you can add constraints on alpha, for example, alpha between -1 and 1. But again, this algorithm, if you never get close to 0, it moves away from 0. So this shows the challenges of MinMax problem compared to the regular minimization problem. And basically, we need to look at it. It has applications. It appears in a lot of other applications. It's more challenging than the regular minimization problem, at least in practice. So we need to look at it. Still, we need to look at it in depth and see what we can do, to understand that what the algorithms are appropriate, what are the best rates that we can achieve for different scenarios. And it's even the first step before going to the algorithms, it's important to understand what should compute, what sort of point we are hoping to compute. Remember, I talked about regular minimization, that you talk about, for example, stationary concepts. Stationary concepts in regular minimization, although you can define it different ways, but typically they are very related, closely related, and people agreed upon many of them from a long time ago. I think from Marcus here, he has papers, I think, in the 70s about first order, second order stationary concepts, 70s and 80s, I think. And from them there till now, people agree. But when you go to min-max optimization, we need to also be more careful on defining stationary concepts. In particular, it is important what viewpoint we have to this min-max optimization, whether we want to look at it as a bi-level optimization, which is on the left, or whether we want to look at it as a game. So in the bi-level optimization or Stackelberg viewpoint, our goal is to minimize a function g of theta, where g of theta is defined as the max of this function. Okay. On the other hand, in the Nash viewpoint, our goal or objective is to look at it as a game, two-player game, zero-sum game between a player theta and player alpha. We want to find a stationary point, for example, or a reasonable point. Let's call it a reasonable point with respect to theta, a reasonable point with respect to alpha. So which one we should take? It's really depending on the application and objective that you have. If we go with the bi-level viewpoint, our objective is to find a theta star, which is reasonable stationary point of G. On the right-hand side, the Nash viewpoint, it tells us we need to find a point theta bar and alpha bar that are stationary or reasonable points of their own utility if you fix the other players' strategy. So on the left-hand side, you are, for example, an epsilon stationary point of G can be defined as saying that in the unconstrained case, you can say that the gradient of G being less than or equal to epsilon. So we are interested in G. We look at G only. So G might be non-smooth in general. So we may smoothify it. For example, as you will see in this talk, we'll replace it. You look at the bounds by Morrow envelope of this G function. So G tilde is the Morrow envelope of it. And gradient, if you have constraints, as we all have in this talk, you may look at different stationary concepts such as proximal gradient, a norm of the proximal gradient being less than or equal to epsilon. On the right-hand side, on the other hand, for example, we can look at first order Nash equilibrium of F, which means that you basically have you're almost stationary with respect to theta and alpha. Sorry, there should be bars here. If we fix the other variables. So if I fix alpha to be alpha bar and I take the derivative with respect to theta, the gradient norm should be less than or equal to epsilon. The gradient norm should with respect to alpha should be also less than or equal to epsilon. And again, if you have constraints, I can replace these with the proximal gradient norms. And these two concepts these two general solution concepts are generally different. It's not hard to come up with examples. This is a very simple example. Okay, I know a lot of you know it, but just to clarify it, these two concepts are in general different, which viewpoint you look at. For example, in this optimization problem, if I have a bi-level viewpoint, I look at this g of theta, which is the max of this function. If I plus this g of theta looks like this. So any reasonable stationary point that you may define with respect to theta is -1. So theta star to me seems the only reasonable point to define. This is, by the way, with respect to theta, it's a convex problem. It's a max of many convex problems. So it is convex with respect to theta. This is a plot of G. So if you look at the bilateral viewpoint, this theta star equals -1 is the only reasonable point that you you should hope an algorithm gives you. On the other hand, if I look at it from a game perspective, and I fix one variable and I want my solution to be optimal with respect to the other, when I fix one, the first order Nash equilibrium is at the point theta bar, alpha bar equals 0 and 0. So you can see that these two solutions are not, they don't have any overlap in this example. And in general, if you're talking about non-convex setting, these two viewpoints lead to different solutions. But there are some special cases that the two concepts coincide. For example, the non-convex concave setting or non-convex strongly concave setting that I'll talk about. These two solution concepts coincide and they are related. For example, when your F is concave or strongly concave in alpha, and the two concepts coincide and are like, I'll talk about that, like how these two are related. So any questions so far about these concepts? Or okay, good.
There is one
question. Are the two viewpoints the same for convex concave? Yes, they are the same. For convex concave case, as long as, for example, under some assumptions, you need to have boundedness of this, that, for example, the constraint. But yes, that the two solution concepts are the same, and you can switch maximum as long as you can switch maximum. This convex concave case, if you have bounded compact constraints. So did I answer your question, Ching? Okay, great. So now that we know these two solution concepts, so now let me talk about a little bit about algorithms and some algorithm ideas. So one that let's say we want to design an algorithm for this, okay, and find this epsilon stationary point. By the way, in this talk, our goal is mostly aiming at the left side. Basically, our viewpoint is the bilevel viewpoint. Although, as I'll talk about that, I'll talk about some special cases. Basically, we cannot solve, at least our results are not able to solve a very general case. We are looking at very particular specific cases, and we have some properties on F. In particular, for example, we assume F is concave in alpha, and A is compact, this set. In that case, there are relations that they can actually, the two solutions coincide with each other. So let's say that we want to design an algorithm for this case, okay? And a natural idea, a simple idea is that I look at this as, again, a g of theta. I look at this max, a g of theta, and then try to minimize g of theta. So let's say I want to minimize the g of theta. What can we do? And we want to, for example, use first order methods because they are dimension free and they use they can be used a lot recent. They can be used easily and they are amenable to like GPUs, for example. So if you want to minimize this g of theta, what you can do is you can simply apply gradient descent to g. Okay, so let's say I want to do this. Which my theta t plus 1 is theta t minus some step size gamma times the gradient of g, and I do some projection because I have some constraint. Now, if you want to do this, you immediately see that, okay, first of all, this g is not in general differentiable because it's the max of some function, so it's not differentiable. Moreover, we don't have access to the gradient of g, we only have access to the gradient of f. But let's start with the case that we can resolve these issues. So let's say that assume that f is strongly concave in alpha. Okay. If f is strongly concave in alpha, then you can show that this g is differentiable in theta. And you can rely on Donski's theorem to compute the gradient of g. In particular, Donski's theorem says that if you want to take the gradient of g, you can look at the max, you can solve the maximization problem Find the maximizer, argmax, and then the gradient with respect to G is the same as the gradient with respect to F. Okay, if you use the maximizer alpha now. And I'm assuming right now a strong concavity with respect to alpha. So we are assuming for any fixed theta, for any given fixed theta, the function is strongly concave in alpha. But your function could be non-convex in theta, but still smooth. Okay. So one idea then for solving this problem would be, for solving this min-max, would be to find an approximate argmax of this. So, and then you apply this gradient descent step with respect to theta. Again, this step, the second step, is mimicking the red iteration, because we know that the gradient of G would be the gradient of F if you compute the exact argmax. But since we use iterative algorithms, we are not able to always exactly find this argmax, but we approximately find argmax. As long as you do enough iterations for solving this, you can find the optimal solution. Now let's understand this. It's not actually very hard to analyze this algorithm. And you'll see that it's easy to show that for example, if your function is strongly concave in alpha, then the algorithm requires order of epsilon -2 gradient evaluations for computing epsilon stationary in terms of the bi-level viewpoint. And why it's this stationary, why we need this many number of iterations? The reason is that we know by classical results that minimizing a non-smooth function, that we are minimizing this G function, which is the max, we need order epsilon -2. So we need this many number of iterations in theta, because minimizing a smooth non-convex problem requires order epsilon -2 iterations to find the first order stationary point. And you can show that to get enough accuracy for your Dunskin's theorem to work, and you are able to get to the max, relate things to the G, get the enough accurate gradient for G, you need to solve this to order epsilon stationary. So this is strongly concave. So the iteration complexity for solving it, depending on, it's basically order, it's linear in terms of epsilon. Okay, so we need to apply k step for solving this. For example, we can apply k steps of projected gradient ascent on alpha, where k is order log epsilon inverse in this case. So in general, we need this many number of gradient evaluation for computing epsilon station. This is, you can show that this is the optimal rate up to logarithmic factor, because even if you solve minimization problem without the max, this is, we need the lower bound is order epsilon -2. This result can relax the strong convexity station, the strong concavity assumption, basically to PL condition type, which requires to establish in Dunskin's types result for under PL assumptions, which can be done. And basically the same rate you can get it under PL assumption. So as long as for any fixed theta, your function in alpha satisfies certain PL assumptions, you still have it. So for example, if your function, as a result, your function is strongly concave, composite with affine in alpha, still you can solve the problem with this iteration complexity. But the next question is that can we relax this strong convexity assumption or PL condition even further? And I'm going to move a little bit, and just instead of assuming strong concave in alpha, we're going to assume that it's concave in alpha. So we are going to assume that it's concave in alpha, but not strongly concave in alpha. So in this case, you can say that G is no longer differentiable. So we lose differentiability of G. So what can we do in this case? A very simple idea is to smoothify G. So basically, for example, we can add standard, like traditional, like smoothifying the max function by adding certain regularization. For example, I can make it strongly concave by adding a lambda, and by choosing my lambda small enough, I can show that computing the stationary point of G lambda can be related to the stationary point of G. And then we can apply gradient descent type on this new function G lambda, which is a smooth version of G. So your algorithm would be this. The algorithm that we have would be something like this. We find alpha, which is the maximizer of, approximate maximizer of this function, regularized function. And then we apply one gradient descent. So we again rely on Donski's theorem. And we can show that actually to get the best iteration complexity from this algorithm, you need to solve this one with a fast iteration method such as Nastro. But you'll see that if you analyze this algorithm for computing this first epsilon first order Nash equilibrium requires epsilon minus 3.5 log epsilon, gradient evaluations for computing first order Nash equilibrium, and order epsilon minus 4 gradient evaluations for computing epsilon stationary to get that stack over. Now the question is, why did we have such a huge rate drop compared to the previous case? Remember, in the strongly convex case, we had the rate which was order epsilon minus 2. Now we had at least, so in this case, we have epsilon minus 3.5. So the question is, why does the algorithm become so much slower when we move from strongly convex to strongly concave to concave? And where does this rate drop come from? And can we make it faster, accelerate? And what's the best rate actually that we can get in this setting? So to understand the rate drop, remember that we are trying to solve this problem to basically be able to use Donski's theorem and like pass on the gradient evaluation with respect to alpha f to the gradient with respect to g. But for your smooth function to be a good approximation of your original function g, your lambda, you can show that it should be order epsilon, okay? Which epsilon is your desired accuracy, okay? Desired stationary concept. And so your lambda should be small. So that leads your G lambda to have, when your lambda is small, this G lambda is smooth, like this differentiable, but its Lipschitz constant, you can show that's inversely proportional to lambda. So it's Lipschitz constant, when you decrease your lambda, your Lipschitz constant of G, of the gradient of G, would explode. So that means that, you have to use your step size, which is small. In particular, your eta step size should be order epsilon. So you're taking a much smaller step sizes. Now your step size with respect to G function, G is this max of this. Then you have a super small step size to make sure, guarantee that you have decrease in every step. And that's one reason that you have a rate drop in your algorithm. That's actually the major reason. So, and we know that when we have, for example, a point, we cannot choose any step size. Depending on your Lipschitz constant, you should have proportion. Your step size should be proportional. Lipschitz constant of the gradient. But we also know that if we can, the look ahead strategy. So if I can look ahead, so instead of using the gradient value here, if I, for example, if I'm moving here, I look ahead and look at the gradient here, that could help me to take longer step sizes. So I don't need to use large step sizes. In particular, we know that this type of update rules, which is the proximal point type update rule, they would work with they would work with any step size. So this in particular, this is equivalent to this update rule is equivalent to doing proximal type update rule. And for the proximal type update rule, we know that for the proximal type update rule, we know that we can use any eta to solve. Give me a second, so I can just give me a second. I'll be back. Sorry for the interruption. So we use this idea of proximal point update rule to modify the algorithm. In particular, we say that what happens if instead of gradient, we try to mimic this iterate, this type of iterate in our algorithm. So what happens if I try to solve this algorithm using basically you use the smoothifying idea that we had, but instead of using gradient descendant G, I do the proximal point algorithm. I use proximal point algorithm G. So if I do this, if I want to mimic this, basically I need by theta t plus 1 and alpha t plus 1, the algorithm, to mimic this, so to approximately solve this problem, okay? Argument of this, I replace the definition of G lambda. G lambda is the max of this. Okay. I need to mimic the behavior of this. Now, this is a strongly convex in theta. If I choose my eta inversely proportional to the Lipschitz constant, and strongly concave in alpha. So you have a problem that's strongly convex now in theta and strongly concave in alpha. And you can switch min and max and min. And now you can see that this inner minimization problem is strongly convex, but my eta should not be order epsilon. This actually, you can show that it should be inversely proportional to the Lipschitz constant. So this inner solution now doesn't have a Lipschitz constant that blows up with your desired accuracy. So you can choose eta, which is order Lipschitz, and that helps you to choose larger step sizes. And analyzing this algorithm, combining with accelerated Nesterov, certain accelerations you can use, show that this idea, if we try to mimic this proximal point algorithm, okay, by switching this, basically solve this inner problem to the desired accuracy by a certain accelerated algorithm, and now use that to do certain acceleration on the outer problem, and again repeatedly do this. This leads to an algorithm that has this iteration complexity. So you get basically much faster algorithm compared to the previous result that we had. And this is so this is this is a fast rate that we could get, okay? And I want to any questions so far before moving to the because next I want to compare this some of the also concurrent and prior art that they also work on the same problem. Any questions? Okay, so I want to quickly also talk about two very closely related works. There are many actually related works, but two works that they are closely related. One, a nice work by Parampil and Jain and Netropoli, 2019, have a very nice result that they show that when you look at this again, when your function is concave in alpha, but possibly non-convex in theta, they could get a similar rate.
So we have a question.
Sure. Yes.
So the question is if you are assuming strong duality on the previous slide.
I'm not assuming strong duality. I'm not assuming a strong duality. You're saying why? Yes. Where you are assuming? Okay, I see. So I'm assuming that your function is strongly convex in alpha. I'm assuming that your function is concave in alpha. So when your function is concave in alpha, okay, adding a small regularization, even lambda, which is small, this makes it a strongly concave in alpha. And when I apply proximal point, this proximal point iteration, this is one step of the algorithm. This one step of the algorithm, this is equivalent to solving this. So this, if you choose your eta small enough, in particular, if you choose your eta inversely proportional to the Lipschitz constant of the gradient, this entire function becomes strongly convex in theta and strongly concave in alpha. Now, if I solve this problem directly, if I try to solve this problem directly by solving the inner problem up to certain stationary, and then the outer problem, use the Nonconvex theorem, solve the outer problem. The problem with this is that, again, my lambda is small. So when lambda is small, the Lipschitz constant of the outer problem blows up. Okay? At least in this analysis, the rate that you get would be slower. But if you switch the max and min, okay, then your inner problem now has a kappa, okay, it has a actually condition number. Right now, your condition number, if your eta is inversely proportional to L, it has a condition number that's constant. So you can solve the inner problem order constant, okay? Okay, it's logarithmic. So let's put it logarithmic in epsilon, okay? And your and you can have it, so you can see that I'm adding a term that the strongly convexity modulus, so your strong convexity modulus with respect to theta, you can make it order L, your Lipschitz constant. So you can make your kappa, which is strong, which is your condition number, to be constant. And that tells you that essentially the inner problem, you can solve it order constant. Okay. And that saves you a lot in terms of where in the previous one, you get your kappa would be in the previous case, if I solve the inner max, this problem, your kappa would be your Lipschitz constant divided by a strong convexity modulus. Strong convexity modulus here is lambda. So lambda should be small. So your kappa is order 1 over epsilon here. And this 1 over epsilon, the kappa, affects the Lipschitz constant of the max, the entire max, the Lipschitz constant of this entire function after the max. And that propagates again back, and you get again order rate of convergence, which is epsilon minus 3 or more. But if you do it in this order, and you use Nonconvex theorem, you can say it in terms of iteration complexity, it gives you 1 order epsilon improvement, because you can solve the inner problem in order constant if you choose your eta, which is inversely proportional to the Lipschitz constant. Did I answer your question, Johan? Okay, great. So any other questions? So let me quickly also compare it with some of the existing works. In particular, the work in 2019 that they consider also the similar scenario that your function f is concave in alpha. They get a similar rate of convergence. But there's a limitation that they develop their own type of acceleration procedure. We use only black box. So we just say that you use this algorithm and you just use Nastro to solve this. And it's more, at least in my viewpoint, because it's much more cleaner. It has less loops in it. It's less number of inner loops in it. Because it's built on existing building blocks. And it works also in the constraint case. We also, the algorithm can, our algorithm be extended to non-Euclidean proximal geometries as well. You can do it. And at the end of the day, it is also a weaker stationary notion. So we showed in our paper that the stationary notion that used in this work and also in Lingen, Jordan, 2020, they are weaker stationary notions. So basically, if you convert to this, is a slower rate of convergence. And they are working in unconstrained case while we are working on constraint setting as well as non-Euclidean proximal geometries. And to give you an idea why stationary notions are different, to give you a quick, very high level idea is that if I just look at the minimization, forget about min-max, let's look at the minimization. The stationary notions that they use in these works are the proximal gradient norm, which is this type of result. So you go, let's say, 1 step of gradient descent with respect to z, and you see that what's the after projection, what's your residual, okay? And you say that if this norm is less than epsilon, then you have epsilon stationary of first type. Let's call it first type. Our works uses this stationary notion that's used also in previous works. Both of these they have used a lot in the previous works, which we call the epsilon stationary of the second type. But what we showed is that this stationary notion, the second type, is stronger than the notion of the first type. In particular, if a point satisfies 2, then it also satisfies 1. So any point that satisfies the second notion is also a stationary point of the first notion. But it's actually strictly stronger notion. In particular, there are problems that given the feasible point z bar, it's epsilon stationary point of the first type. So it's just, but it's not the stationary point of the second type for any epsilon prime less than or equal to square root epsilon. So there is an order of magnitude difference between the stationary point notion that's used by this notion rather than the first notion. But I won't go through a lot of details of it. You can find the details in our paper. There are some also at the end, I want to also mention that there are like very close other closely related parts works by, for example, Kang Montero, that they did. They also looked at the case that F is concave in alpha, but they assume that they have access to the gradient of the max, which is in many applications is not feasible. So to have the gradient access or like similar to gradient access, subgradient access to this max function, which actually this has been resolved in Zhao's work. Also, so any questions? So the next thing that I want to address, I want to say that can we go beyond the non-convex concave setting? So far, assume that the function is non-convex in theta, but I assume always that you have concavity in alpha or strong concavity in alpha. So the natural question is, can we really go beyond it? And there is like, I want to, because I'm approaching the end of my time, I want to quickly tell you about other work that we did. And it's based on a very simple observation that there are two other relatively easy cases. So in particular, you can show that, you can see that if the problem with respect to theta and alpha are decoupled, this problem is easy, right? Because it's two different problems. Another case that's easy, that's an immediate observation, is that when your constraint set A is, for example, singleton. If it's singleton, this is basically a minimization problem. Okay, this is not a min-max problem. So this observation make you like you can simply say that, okay, can we relax these two cases a little bit? And you can show that actually you can relax these two conditions. In other words, instead of this case, you can show that if the coupling between theta and alpha in this objective, if the coupling is small, okay, you can still solve the problem efficiently. And you can show that if your example 2, if it's not singleton, but it's a set with a small radius. So your A set, as a constraint set, has like a small radius, but still you can show that the problem is solved. In particular, we show this result that if, so this L theta alpha, you can think of it as the bound that you have on the second order derivative, where you take one derivative with respect to theta and another derivative with respect to alpha. L alpha alpha is the second order, the bound on second order derivative, and you take two derivatives with respect to alpha. This L theta theta is when you take two derivatives with respect to theta. D alpha is the radius of your constraint set A. Okay. So in this case, if this bound is less than the accuracy that you need, okay, you still can solve the optimization problem efficiently, even though your problem could be non-concave in alpha, could be very general non-convex, non-concave, but you can solve it up to desired accuracy. And the reason is that, when this bound is satisfied, we were able to show that solving this problem, actually first order approximate solution of the problem with respect to alpha. So we approximate the objective function with respect to alpha. Solving this problem gives you a stationary, finding a stationary notion in this problem is an epsilon stationary in the original problem, because your radius is small, for example. When your radius is small, the alpha is small, then your approximation is a good approximation of the original function. And that leads to an efficient algorithm. And you can see that this happens, for example, when your d alpha is small, meaning that the radius of the set A is small, or the diameter of the set A is small. This corresponds to the extension of the case that this is singleton, or your coupling is small, meaning that L theta alpha is small. And this can be viewed as a case as the extension of this setting. And this idea can be, I'm presenting it for a first order approximation. You can get like a little bit tighter, actually you can relax this condition a little bit by going for higher order approximation. You can go, for example, for second order approximation. In that case, again, you can solve the problem using the ideas of trust region method. And you have a relaxed assumption on the diameter, can still get efficient algorithms. And you can find the details of it in our work. I'm not going to go over it, but you can find the details on this work. And the natural question is that, is it useful? For example, can we have an example that the radius of this set is small? It's actually, a lot happens in defense against adversarial attacks and neural networks, because the attacks is, as I mentioned at the beginning, the changes in the input that you need your algorithm to make it robust is very small. So in those cases, the diameter of the set A is very small. On the other hand, you don't need to solve the problems typically to very accurate solution in the training error. What matters for you is the test error, and we typically don't go for getting very, very small training error. So we can stop early. So we don't need epsilon small. So our epsilon is large in that application, and d alpha is small. So with that, I want to also mention a little bit that some of these ideas can be extended to zeroth order method. How much time do I have?
1 minute.
1 minute, okay. So I quickly want to mention that we apply these results to defense against adversarial attacks in neural networks, and I'm going to skip some details. And we can show that the algorithms that you can get algorithms that they perform much better than perform better in the test phase than some of the existing benchmarks. We also applied it to fairness learning, fairness and federated learning, and other contexts, fairness in machine learning. So with that, I would like to conclude. So we also applied to GAN. So basically the applications that we started. So I want to conclude and say that I hope that I convinced you that these problems are important, although they are difficult. This class of problems are challenging, but they are important. They have many applications. Special cases of it can be solved efficiently, the very special cases, but there are still many open problems. I want to conclude by saying that there are a long histories on MinMax problems, especially if you look at it from game perspective. There are a lot of early works that they use in monotone operators. They look at these problems. Sorry. There are also, I want to say that, so that has a long history. I want to also say that there are a lot of recent works that I may have missed on this application. I'll list some of them here, but I definitely have missed a lot here. And I only compared with the closest one, but in our papers, you can go and look at that, many of the existing works that I list here. These are some of the references of basically the works that I talked about, and some of the resulting application works. And the codes I then talked about applications, but if you're interested in them and the codes, they are available here. With that, I would like to conclude. Thank you very much. And if you have any questions, I would be happy to answer.
So, Meisam, thank you very much for a very interesting talk. Are there any questions? Then let me ask first question. Yes. So one of the methods. Okay, let us start with the method where you just use the smoothing approach, yeah, by fixing the parameter lambda. So is it probably better to also to update lambda in every iteration, or you have to fix it and to choose it? I mean, in order to be as high as the error.
That's a great question. That's a great question. Okay. So the question is that you have this lambda in your algorithm. You choose your lambda, you say that you have to choose it depending on the desired accuracy. I mentioned that I have to choose it based on the desired accuracy. You choose basically lambda small at the beginning. You choose lambda small enough, and that is the reason they get the slow rate of convergence. Can you adaptively change it? Basically, choose lambda small at the beginning and choose lambda large at the beginning and maybe decrease it toward the end. So the answer is that we tried it. Okay, in practice it helps you, but we couldn't get, at least with this naive idea, we couldn't get a better rate of convergence with adaptive choice. So we couldn't get a better rate of convergence theoretically, but in practice it helps.
Okay.
So there might be a better analysis or someone coming up with a tighter analysis showing that it's better.
Okay.
So there are two questions.
Thank you. Yes. So then probably they would like to just to ask the question and to unmute the microphones. Or should we read the question? Sometimes it's better to have some interaction. Okay.
Yeah.
So
I can ask the question.
Yeah, please. Sure.
Thank you for the talk. So I'm not an expert in these problems. So I had a question. Is there a simple, sufficient, and necessary condition for these two types of stationary points to agree? Like if we look at non-strong duality or something like that?
Okay. So the question is that you have this viewpoint on the left and this viewpoint on the right. Is there a simple, or like, is there sufficient and necessary condition for these two to agree? I know there has been a lot of work in the literature for min-max problems, and the game perspective would be the same, but I'm not aware of like necessary and sufficient conditions that works like at least a simple necessary and sufficient condition that's easily checkable for the function. But for cases like, for example, convex concave, or when you have convex concave plus compactness of the feasible set, or when you have strong concavity with respect to alpha, these two would coincide. But I'm not aware of any like general simple condition that can easily check it.
Okay, thanks.
Okay.
Thank you.
Yes. Can I ask a question?
Sure.
Yeah, thank you for your talk. I just have a question. So basically, maybe I missed something, but so is the problem of finding a stationary or equilibrium point, I don't know, is in the full non-convex setting when, I mean, we don't have any additional assumptions about, I don't know, that alpha is the singleton, or is it still an open problem, or there's
That's a very good question. Is it still an open problem?
So we don't know. It's yes. Yeah. Sorry. Yeah.
So that's a great question. So let me a little bit rephrase it. So do you have this min-max problem? I have this min-max problems. You have this min-max problem. Is finding a stationary point in any notion possible with reasonable iteration complexity with an algorithm that's not exhaustive set? And I would say yes, it's still open. There's no algorithm that can solve it like the general case. There are some hardness results. For example, there's a paper by Daskalakis that they show that certain Nash viewpoints, stationary viewpoints, for certain types of constraint, the problems are difficult to solve. This problems is basically you cannot get rid of the polynomial you cannot get rid of cannot get the polynomial dependence on the dimension, for example. You have to pay something somewhere. You either need to go exponential in terms of the dimension, or you need to go exponential in terms of 1 over epsilon being your desired accuracy. So, but that's again for certain types of Nash viewpoint stationary, and it's again for certain type of constraints. There are some stationary concepts that it has been shown that it's easy to solve. Let me see if I listed the references here. Okay, there are, sorry. There is, okay, I do not. Okay, unfortunately, I don't have the. Okay, this is the Daskalakis work that I talked about. Okay, there are. Okay, let me take a step back. There are also some results that they define certain stationary concept or certain that it's easy to solve, but those stationary concepts are not at least relatable to the classical stationary notions, even in the minimization problem. So basically, it's either the cases that solve, it's either showing difficult or either relaxing the stationary notion a lot so that it's computable. So I would say, yes, the problem is still open and it's not known an algorithm.
Okay, thank you very much.
So there is one, sorry.
So we have,
go ahead.
So Meisam,
yes.
Go ahead.
So there is one more question I wanted to in the chat. Is there a simple class of scenarios that we can have an explicit closed form solution? Okay, is there a class of problems that you can get the explicit closed form? You mean for the MinMax problem?
Yeah, I guess so.
Okay. Let me think about it. Okay, well, there are some cases that you can build. For example, if you have, I can think of, right now I'm thinking out loud. So if I have this MinMax, this is quadratic F, okay? And it has a closed form, this inner problem has a closed form, you can plug it in. And if your dependence on theta is so that you also get the closed form, okay? And theta then, so for basically linear in theta, for example, and quadratic on alpha, I would assume that you get a you can get a closed form solution. Okay, so, but I don't know anything from top of my head that you can get like a very easy closed form. I can think that right now, for example, if you have quadratic in alpha, okay, strongly concave quadratic in alpha, and this is a simple case that you can plug in the optimal alpha and get the function in theta. And if you choose, for example, your theta dependence on theta and alpha correctly, you might be able to get a closed form.
Okay, thank you.
So are there other questions? I would have another question, Meisam. So can you please go to the algorithm where in the first iteration, you just did an argmax, and then in the second iteration, did a gradient step?
The concave case or strongly concave case?
Yeah, the concave case. Let's go for the concave case.
Okay.
This was, I guess, yes.
Okay. This is the algorithm, right?
But actually, it was the previous slide, I guess.
This one, or this is the strongly concave, but that's
this one. Okay, this one. Let's stay with this one. Okay. So talk about the first argmax. So if you would do just one step, one gradient step, gradient as the step, then we would get something which doesn't converge in the convex concave case. instead of doing k steps, yeah, let's do just one step.
Once. Yes.
So we know that this algorithm, it's shown here with the counterexample, wouldn't converge in the convex concave case.
Yes.
But what about doing this in the non-convex concave case? I mean, is it clear that you have to do k steps?
That's a great question. You can get convergence actually under some assumptions when you do also one step.
Okay.
There are like some works by Mingyi Hong and others, I think, that they have that they showed. For example, there are some other also works, I think, by Lin, Jin, and Jordan. I think actually, it's that they show that one step could also you can get convergence. It's a very good question.
Just to avoid inner loops. I mean, inner loops.
Yeah, exactly. Inner loops are more difficult. Inner loops are challenging to implement.
Yes.
And the idea behind it is that if you do one step, you can think of it. It goes back to your, maybe it's connected also to your previous question, that if you do one step, you can think that you're solving this problem up to certain stationaries, up to certain accuracy still, okay? So that gives you like some gradient that's still accurate enough.
Yes.
And you can show that it's strong in the concave case. It still can work.
Yes. Okay.
And it's more practical because its inner loops are more difficult to challenge.
Yes, I agree. Okay, great. Other questions? So then let us stop here. So Meisam, thank you very much for a great talk. So we had a great discussion today. We had many people in our Zoom room. Yeah? So a lot of interest in MinMax algorithms. So I just want to announce that we will post the video and the slides of the talk on our website. And also to let you know that our next speaker is Ying Kui from University of Minnesota. This was today's talk. So we are looking forward to many interesting talks in the next weeks of our seminar. So we are still online. We hope to go back to normality, but this probably will take months or hopefully only months. So thank you very much. Have a nice day. Have a nice afternoon. Thank you, Meisam. It was a great talk.
Thank you. Thank you for coming. Bye-bye. And thank you, everyone.
Bye-bye.